Recording in progress.
Hello guys. Okay. Okay. Whoa, wrong screen. Okay, great. So we're on a new section of the course today. Well, it's still graph theory, but we're going to talk about different kinds of ways of thinking about a graph. And so this one is motivated by, I guess, a fun story of how sometime maybe about 100 years ago, there was a Hungarian sociologist, and the Hungarian sociologist made an interesting observation as they were analyzing classrooms of people. And so this sociologist observed that if you go and look at any classroom of about 20 kids, among every class of about 20 kids, right? Somehow you're always able to find out that the nature of human social interaction is you can always find at least one of these, at least one of two options. You could either find 4 kids who are already pairwise friends with each other. 4 kids. All 4 choose 2 pairs are friends. We're going to assume that friendship here is mutual in the sense that if you have 2 people, then they are friends or they are not friends, like that. Or you can find 4 kids. None of the 4 choose 2 pairs are friends. Okay, so this was kind of nifty. This Hungarian sociologist was kind of like going through classrooms and finding out that, this is just a nature of human behavior somehow. Like they always have this situation where you can find friends, like groups of 4 who are friends, a group of 4 who are not friends. Something to emphasize here, this word or, in mathematics, or means can be both. That's why I emphasized that up here it's like at least one of these are true. So whenever we use the word or, we mean inclusive or. So that's like the inclusive nature of the word or. Okay, but fortunately this person was Hungarian. Hungarians know a lot about combinatorics somehow. And the story goes that this person was also friends of some other famous Hungarian mathematicians. And this person actually figured out that, it has nothing to do with kids. It's just a true statement about whenever I have any 20 vertices, then I can always find interesting situations in the graphs. So actually, it turns out that this observation it's actually a fact. Actually is a fact about graphs. It has nothing to do with kids, nothing to do with human relationships. That every 20 vertex graph contains a complete graph with 4 vertices. That's this K4. Remember what that means. I don't know. I don't remember if I actually defined it in this class yet or not. But this is 4 vertices, and all 4 choose 2 edges. Or it contains the complement of K4. It's hard to decide what to use for this notation. Sometimes people do it with a bar on top. I guess that's what I'm going to do this time. Sometimes people do it with a little C for complement. But what this K4 with a bar means, that just means 4 vertices with really no edges inside there. I say the word in because if you have these 4 vertices and like there's an edge that goes from one out to another, that's okay. All right? So that's the situation. That somehow you either contain a K4 or you contain the complement of K4. Actually, that is often called an independent set. So this thing up here is an independent set of size 4. Of 4 vertices. Okay? So in that case, what we have here is that somehow this is true. And we're going to go about thinking about this. But there's a deep question. It's like, do you really need 20? Well, I don't know. Do you think it's true if I try to say the same thing with like 5 vertices? Could it be true that every 5 vertex graph always has a K4 or like independent set of size 4? That feels kind of ambitious. It's actually probably not true. Probably not is the right answer. It's like, yeah, it's not. And we'll find some good reasons why it's not. But the interesting thing that you should naturally wonder here is like, do you need 20 for this to be true? And this entire area that we're now talking about is called Ramsey Theory. Ramsey Theory is this thing where we're talking about just because I have a lot of vertices, is there going to be a big clique or a big independent set? This is called a clique. K4 is called a clique. Let me just put that word here because we're using it now. A big clique or a big independent set. And specifically, actually, this is an interesting question. And you can define what's called the Ramsey number. And the Ramsey number is the smallest number of vertices for which this is true. So let's define that now, because we're going to be talking about Ramsey numbers today. Whoops. Okay. The Ramsey number, RT, T, is defined to be the minimum number of vertices needed to guarantee there is a KT or an independent set of size of T vertices. By the way, actually, even as written right here as a definition, this is not a legitimate definition. Can anyone tell me why this is like a bad thing for me to say that this is a definition, that there will be a minimum number of vertices required to guarantee a KT or a clique or an independent set of T vertices, and I'll call that RTT. What's bad about this definition out of it?
You have no idea whether this actually exists.
Oh no, what's up with this min? That's bad. I shouldn't have called it a def. Actually, I should have called it a theorem. There's a theorem called Ramsey's theorem, which is that this exists. So I should actually say there's actually a theorem. The theorem should precede the whole thing, which says that the Ramsey numbers exist. It's like, you know, if somebody told you, there's a way, just get enough vertices in the world, and there will be a K100 or an independent set of 100 vertices. How do you know? Like, what if somebody could like make a really wacko graph and it has no clique of 100 vertices and has no independent set of 100 vertices? Maybe that's the case. And so the fact that this even exists is a theorem. And specifically, I want to say, how would you know that enough vertices would guarantee KT or KT bar? I will say this reminds me of a conversation I once had with somebody who was not a mathematician, and that person was asking me, what do you guys do in math? And I said, we prove stuff. And they said, what do you mean prove stuff? I said, you know, for example, we prove there are infinitely many prime numbers. And the person said, but of course there are. There's so many numbers. So yes, I mean, in some sense that is the case, but I would have, you know, like, it's just like, that's not a proof, right? And so what's going on here is a similar kind of concept. Ooh. So somebody asked, do I mean K? Yeah, okay, so somebody said, why are you putting the T and the T? I use the same variable twice. So specifically what's going on here is that there is a notion of what's called diagonal Ramsey numbers, which is when I want to have both T and T, both of these are T, the clique and the independent set, both T vertices. Then there's a notion of off-diagonal Ramsey numbers, which is if I go and say, I want a clique of 5 vertices or an independent set of 7 vertices. And you could ask those kinds of questions too. That's just why it's the same T here. And just because we are using, I guess, colors, I'll just emphasize that they have colors. Oh, actually, in Ramsey theory, the standard colors are called red and blue. We're about to get that. So I'm just going to go with red and blue. So this is the part where colors are very handy when you're teaching this class. So notice I said something about colors. It's because there's a way to rephrase this. Another way you can see Ramsey numbers talked about is not to say, hey, just get any graph of that many vertices. Instead, you can say, suppose I take that many vertices and I make every possible edge, but I color every edge in red or blue. So I'm going to write equivalently. RTT equals min number vertices such that if every possible edge is red or blue, you run into my shirt. Then you get like a monochromatic, like all the same color, KT. Get, how do I write this? Let's go up here. Monochromatic KT. I'm going to attempt to stand out of the way. So the deal here, actually somebody once told me you should just wear a green shirt when you teach and then you can have more space to write. But that would just be extremely strange for you guys to watch. Because I'm in front of a green screen, so that would just make all of this part invisible, and I could write on it too. Anyway, so now over here, this is the same statement, by the way, of saying if you just color everything with one of two colors, red and blue, then you want to have a monochromatic, meaning all the edges are the same color with T vertices. The reason is because if I have a graph, I can think of a graph as coloring the possible edges with two different colors. When there's an edge, it's blue, and when there's no edge, it's red. Like red stands for missing or something. Somebody just put an interesting comment here. Oh no! Oh, okay, I should have done that on April 1st. Yeah, you know what? You guys are very clever. Okay, right. So this is the notion of Ramsey numbers, Ramsey theory. Let's go and dig into some Ramsey numbers now. Okay. So again, the Ramsey number is the smallest thing you need to guarantee something. And I'm going to think of the colored version. It's a lot easier to do this with colors than to think of it as edges there or not there. So let's start to mess around with this. What is R11? I'll just write that down. Minimum number of vertices such that if all edges are colored red or blue, there's a monochromatic edge K1. I wanted to emphasize monochromatic edge. The edges are what you're coloring, not the vertices. What is this? I claim this is so easy I can do this. What's the minimum number of vertices you need so that no matter how you color all those edges, you're going to find a K1 where all the edges are the same color? Equals. If you want to just bang it in the chat, that's fine too. Okay. So now this is tricky. It's like, what does it mean a K1? Well, okay, so the thing is like, it's either 1 or it's 2, but it turns out this is 1 because it's like there. I did it. I got 1, and that 1, it already has a monochromatic K1. And that's it right there. So that one's okay. That one's done. Let's do some more. R2, 2. Now it gets a little bit less obvious. Well, I mean, slightly less obvious. What would this be? What's the minimum number of vertices so that as soon as I have that many vertices and you colored all the edges like red or blue, 2? Yeah, let's try 2. Let's try 2. It is actually 2 since now I'm going to say like, I'm actually going to say I have to show two things, right? In order to say that it's equal to 2, I need to say if I have 2 vertices and I anyhow color, if I have any coloring of the edges on 2 vertices, there's a monochromatic K2. There's a monochromatic K2. Well, that's obvious because it's like if I have 2 vertices and the edge, bang, it's there, right? It's just whatever you colored it, that's monochromatic because there's only one edge anyway. But I also need the other piece. The other piece is, and actually, can someone help me explain what the other piece is? If I want to say that the minimum number is 2, on the one hand, I have to show that whenever I have 2, any coloring, I'll find that monochromatic K2. What's the other thing I need to do? Braden.
You show it can't work for smaller numbers?
I need to show it can't work for smaller numbers. That's right. I need to show that this conclusion can't work for smaller numbers. Can you help me say that in like in English? That's like not just how would I show that it can't work for smaller numbers?
You have to show that there exists, in this case, a graph on one vertex.
Yes.
That there's no clique of 2 or independent set.
Yep. there exists a coloring of the edges on one vertex where there is no monochromatic K2. Did that make sense? I'm just really being very clear to split the two. On the one hand, you need to show, any coloring in the world on this two vertices, on the edges on the two vertices, you'll find the monochromatic thing. The other thing is like, hey, just find one. Show me one coloring, and I'm done. Like, if you can feel the asymmetry here, the thing on top, you got to prove something. And on the bottom, you just have to be like, hey, look at this. So at first you might, when I say, hey, look at this, I'll do that one right now. Here, this one. Bam. One vertex, I colored all the edges, and there's no monochromatic K2, obviously. So I'm done, right? And the other one I have to make some, well, this one was obvious. There was a way to argue. That's okay. But I wanted to emphasize that there's some asymmetry here. And a priori, you might say, this looks harder. Maybe it's hard to go. Sorry, a priori, this looks easier. Just like, show a coloring, darn it. Okay, somebody had made a comment. Just, could you ask your question again? Because I don't understand it.
On the previous page, it said Ramsey number RT equals minimum number of vertices needed to guarantee there's a KZ. Why is it Z?
It's because my handwriting is awful. It's a T. Okay, I'm sorry. That's my fault here. Yeah, that's a T. Okay, but thanks for asking. And in general, if my handwriting is lousy, please let me know. Yes, I'll try to do a better job. Okay, but now we're going to get to the first interesting ish theorem in Ramsey theory, R33. Okay. Now, if I want to do this, actually, I'm going to give a hint, which is I already indicated drawing an example of something which has no monochromatic K3 is probably the easier way to go. Can someone come up with a way to draw a graph? Sorry, it's going to have a bunch of vertices. You're going to have colored every edge red or blue, and there better not be any monochromatic triangles. Can anyone come up with one of those? Advait.
Can you make a graph with no monochromatic triangles with 5 vertices?
How? Let me draw 5 vertices for you. Tell me how to color it.
Well, just put down one color randomly.
One color randomly.
And then just keep going, and then just break triangles every time you have the chance to make them.
Oh, okay. Okay, I get what you said. What you said is just randomly add edges, avoiding triangles. Is that what you mean?
Pretty much.
So I will say, it ran into my head again, you have just discovered something called the triangle-free process. That's actually, there's a name for what you have just said. It's called the triangle-free process. In fact, our current department head of mathematical sciences at Carnegie Mellon, Tom Bowman, he's a really good guy. You should take his class at some point. But he actually has some papers on the triangle-free process, where he was one of the people who analyzed what would happen if you did this in a large number of vertices. Interesting stuff. And actually, just to let you know, the reason why he was interested in that is because that's related to R3, T. Here we're doing R3, 3, which is obviously this would make a lot of sense. But I'm just saying what you did is people were interested. People were interested in that. That's an interesting area of research. Okay, so I'm just going to start doing it, all right? Yeah, why not? No triangles. Now what? Uh-oh.
Make the rest of them blue, maybe.
But now we got trouble.
Oh, yikes.
Oh, yikes. So I think what this is showing is that the triangle-free process, by the way, it is a good strategy. It's a very interesting way to do things for large graphs. But the oh, yikes is So that didn't quite work. So what if you made one of those blue at the start? You mean like this?
Yeah.
Yeah. So what we're doing right now is we're getting out of the triangle-free process. We're going to try to be smart. Sorry, not that you weren't smart. Your idea is very good for a different kind of thing. But here we're going to cook something. We're going to say, let's let other people get involved. It is true you can do it with 5. There is a way to color all 10 edges of this K5 in a way that avoids triangles in any one particular color. Does someone else want to try? And that one won't be random. It will actually look really nice. It'll be a nice pattern. Someone raise hand. Anyone else want to try? It's not that bad. Jack.
Maybe you can put a balloon around the edge.
Ah.
And,
Oh yeah, this is actually a really neat fact, by the way. Did you know that K5 breaks into a star and a pentagon? It's kind of nice. And like there's no triangles, right? Oh, emphasis on what a triangle means. Triangle means K3. It means 3 vertices where I have all the same color edge between them. Even though you see some triangles in this picture, those are not triangles in the graph. Those are just because I drew it and the lines crossed. All right? So this is one. So what we just found out is that, hey, it's possible to make 5 vertices and a coloring of the edges, so there's no monochromatic triangles. Can anyone tell me what that means in terms of R33? R33, we claim, is going to be a number. Now you stare at this. That tells you a fact about R33 compared to 5. What is that fact? And when I was learning this subject, I always, like, my brain swims about inequalities or like strict inequalities or non-strict inequalities. So I wanted to actually ask everyone to play in this and think to yourself, what would that mean? I want to say something about R33. Yes, Charlie.
I think that R33 must be strictly greater than 5.
Okay, good. So it must be strictly greater than 5 because of the fact that you're talking about the minimum required to guarantee something, and 5 doesn't guarantee it. All right? So what we have here is 5 can't guarantee. I can't spell guarantee. How do you spell guarantee? I did it a few times already. Guarantee. Can't guarantee a monochromatic K3. I'm getting shorter, just calling it mono. So that means that 5 is not good enough. That means R33 is bigger than 5. Well, the Ramsey number would only be an integer. So that's the same as saying it better be at least 6. Okay? And the interesting thing is that actually 6 is enough. So let's go to the next screen. Next screen is but. Any coloring of the edges on, I'll write on 6 vertices with 2 colors has a monochromatic K3. Now that's cool. That's going to tell me that R33 is 6. And how would we do this? So the way to, Advait, what do you want to say?
Can you like pigeonhole it or something?
Yeah, let's pigeonhole it or something. Okay, so I have like 6 vertices, right? So just like pull one aside. It's like here, one of the vertices. Any one vertex. Great. So I've got this one vertex. How many other vertices are out here to look at? There's 5 other vertices to look at. Right? So the way I'm thinking of it is I've kind of separated off this one vertex from these other 5. When you say pigeonhole, could you be a bit more specific? What do you mean by pigeonhole?
So like from that one vertex, you have at least 3 of the same color.
Ah.
Other vertices by pigeonhole.
Okay. So what the idea here is that you have 5 other vertices. So at least 3 of them are adjacent via the same color. Oh, let's give that vertex a name, V. Okay? Are adjacent to V via the same color. Okay. Well, now this is one of these places where we like in mathematics to say walog without loss of generality. So which color? I mean, it's going to be the same for both of the arguments. But because there's nothing special about the colors yet, let's just go and say, you know, here. Walog red. And I'm only going to draw 3 of them. There might be more of them. Like, it might be that there's more adjacent by red, but let's focus on these. Focus on some 3 of them. Right? By the way, walog means without loss of generality. Once somebody was explaining this on the board and called it without lots of generality, and that would be the exact opposite. So the L stands for loss. Without loss of generality. This is one of these wonderful statements in math that you can say when you're like, it looks symmetric enough. and that is the case. And the only way to know, like, yeah, this was a legitimate thing to say is because at the end you'll say, well, but obviously if I just had them blue instead, I'll just flip everything in the argument, okay? So can someone else tell me why this would be awesome? So I've just drawn that here's this one vertex, here are these three with red across to the right. Can someone else tell me how I'm going to use this to go and get a monochromatic triangle? I just want more people involved. This is a perfect setup. Braden.
Well, now we know that none of those three vertices can have a red edge between them. Because if we do, that creates a triangle.
So the important thing is that, look, if I put a red edge on any one of these, bang, I have a triangle. Okay, let me write that down first. If any of this thing, these kinds of edges, are red, then a K3. Let's use red. It's a red K3, so I'm going to actually just write the K3 in red. Then I got a K3, red K3. Okay? Okay. And that would be great. Then we're done, right? We're trying to show that there's always going to be a monochromatic triangle. This would give me done. Well, then there's the else. Else all three are blue. What's that? Oh, that's a blue K3, right? Because that's a K3 right there. Three vertices and all three of the edges are blue. Blue K3. And you're done. So that's actually how this works. And without loss of generality, the log was like, well, come on. If I had that the three were blue instead, then I'll just do the same argument. I'll say if these were all blue, then each of those white shaded edges, if any of them is blue, I'm done. I got a blue K3. Otherwise, it's red, and then I got this. Otherwise, all of them are red, and I got this red K3. Did this argument make sense? This is this R33. Every 6 people at a party, there's always 3 of them who already knew each other before, or 3 of them who didn't know each other, didn't know each other, didn't know each other before. Really, really satisfying. This is actually often what I'll say if I was, I used to travel a lot, and if somebody would ask me, what do you do as a mathematician? We prove things. I'll give this example too. And this is something you can explain to someone. You can just be like, here's how I would prove it. And you don't have to draw all of the possible ways of making, friends or not friends on 6 vertices, which is a lot of possibilities. Okay, did this proof make sense? Because now we have just proven something about R33. So R33 equals 6. Because once I have 6 vertices, okay, for sure, you'll find the monochromatic, whatever. And if I have less than 6, not good enough for guaranteeing. We saw that pentagon with a star inside it. Well, then now it's interesting. It's like, how about all the other Ramsey numbers, like R44, R55, R66, and so on? Well, there's a fun statement about this. First of all, R44, I don't remember what it is. I'm not sure what it is. Somebody can probably look it up. Is it like 17 or 18 or something? It's definitely less than 20. But as you can see, I don't pay too much attention to exactly what the numbers are. You might say at first, oh, what is it? I think it's 17. Maybe it is 17. Okay, thanks, Eric. So it's like, yeah. The reason I give 20 is like, I'm sure 20 is enough. But you might say, oh, come on. Such small numbers. Let's just make a computer search, right? That can't be too hard. It's like we know R44 is 17, and then there's R55, R66. How hard could it possibly be to do a computer search? Like R55, that's probably somewhere around like 50-ish, right? So why not just go and attempt to prove this by exhaustion, called find all the possible colorings of graphs on 50 vertices. And just show, like, exhaustively that they always have monochromatic K5s. I'll write to show. I actually don't know what is R55, but I'm just going to say to show R55 is less than or equal to 50. Okay. Aha. So if I wanted to show it's less than or equal to 50, because suppose I want to get an answer, right, to find R55, let's just say to find R55. I don't want to say to show R55 less than or equal to 50. It's to find R55. You just need to find some particular coloring of edges on some n-1 vertices with no monochromatic K5. Computers are awesome. Surely they're powerful enough. And check every coloring of edges on n vertices to see they have monochromatic K5, right? And in this particular case, n happens to be, I think, around 50. You guys are much faster than me and checking things on the internet, but I think it's around 50, right? It's like here, n is somewhere on the order of 50, I think. Maybe it's 60, maybe it's 40, it's something like that. But now I already see people posted into the chat. Uh-oh. The number of colorings is like 2 to the power n choose 2. Because like every edge, every possible edge is one color or the other. I wrote some approximately because maybe you could say there's some symmetry, right? Maybe you don't need to worry about every coloring, but unfortunately there's not enough symmetry. And so that would be 2 to the power 50 choose 2. And 50 choose 2 is about like 50 times 49 over 2. That's approximately 50 squared over 2. So that's like 2 to the power like 1250-ish. That's bad news. So unfortunately the computers aren't this fast. Oh, people wrote some stuff. Ramsey R55, 43 to 48. Yeah. So you see, in my head, it's like somewhere in the 40s or 50s. Nobody knows. And thanks, Chris, for posting that. So, yes, so thank you very much. What you just said is it's like 43 to 48. Something like that. By the way, actually, these Ramsey numbers are quite neat. There's a story about this where Paul Erdős, I think, once had a quote where he said, if aliens showed up in the world and said they need us to tell them R55 or they'll blow up the planet, then we should rally all of humanity's computers and mathematicians and whatevers, and we could probably find a way to do this. Maybe. Even though this is huge, we use symmetries or whatever, we might be able to do it. But if the aliens ask us for R66, we should just try to blow up the aliens. So that's the quote. The R66 is like out of reach. Actually, if you look at these bounds on Ramsey numbers, you will see that some of these papers have a person named Mackey on them. That's the same Mackey that you know. So yeah, if you look at these like bounds on Ramsey numbers, John Mackey actually was involved in some of these. So okay, this is just showing you our department here at Carnegie Mellon is like touching this particular subject quite a lot. Now, great. Now that we know that these particular numbers are hard to actually find, let's at least show that they're finite. Let's prove Ramsey's theorem. Okay. So let's go and prove that the Ramsey number is finite. It's not that big. Sorry, that's the wrong word. It's not infinitely large. Okay. So what we're actually going to show is we're going to show a lemma, which says that the Ramsey number R S comma T. And that's why I used this like 2 parameters. It ends up being very helpful that there's 2 parameters here. It's less than or equal to the Ramsey number of S minus 1t plus the Ramsey number of S t minus 1. Okay, when I was learning this, I always found it hard. Like, what's this inequality? Let's translate that into words. I.e., what does it actually mean? It means that whenever I have the right-hand side. Whenever you have the right-hand side, R S minus 1t plus R S t minus 1, that many vertices, and you look at any 2 coloring of all possible edges, you have, I'll write a red KS or a blue KT. And that's a T, not a Z. So that's the statement. The statement is that somehow if I just get enough vertices together, I can guarantee myself a red KS or a blue KT. And the interesting thing here is we're establishing the next bound, like the next Ramsey number, is sort of dependent on some previous Ramsey numbers. By the way, this will be enough to show that they are all finite, because you can build any Ramsey number from smaller ones using some base cases. Let's also use like some obvious facts. Also, this is more obvious, but if I ever have R1 comma t, can anyone tell me what this is? How many vertices do I need to guarantee that there is always a red K1 or a blue KT? 1. You put 1 down, there's your red K1. That's very satisfying. And what if I had RS comma 1? Well, same reason, that's a 1 also. If I wanted to have a red KS or a blue K1, one vertex, you got your blue K1. So what this is it's sort of setting up like some base cases for you to show by induction that this Ramsey number is always finite, which is satisfying. Okay, let's go and prove this lemma. I claim that the proof is very similar to what we did with R33. Advait.
But what if you assume that it works for the two things that you're adding, and then just look at the complete graph with that many vertices? Pick out one vertex and then like see how many red and blue things are coming out of it.
Okay, let's try that. So what we're going to do first is we're going to say, hey, we're supposed to prove this IE, right? Whenever I have this many vertices, give me that many vertices. Suppose I'm staring at an arbitrary coloring of the edges with two colors. I call it arbitrary two coloring because at some point we might talk about using more number of colors. But anyway, I will. Oh my gosh, I even already wrote that. Okay, so this two coloring, that means that I'm using two colors. My gosh. Okay, I didn't mean to add new terminology so early. But two coloring means using up to two colors. That's the technical lingo with this Ramsey theory, because there can be multicolored Ramsey theorem too, with like 15 colors or something. But the proof of the lemma, back to this, is like, okay, consider an arbitrary two coloring of that many vertices. An arbitrary two coloring of all edges, all possible edges, among that many vertices, r s minus 1 t plus r s t minus 1 vertices. Okay, and let's pull any vertex out. Any vertex. Just take one of them aside, and we'll do what we did last time. Chop it off and think about everybody else. Wow, there's a lot of the other ones. But what you want to do is you want to say of the other ones, some of the other ones are connected, are adjacent to this vertex V. Let's give it a name. Some of the other ones are adjacent to V via a red. And some of them are adjacent to V via a blue. So I have some adjacent via red, some adjacent via blue. Actually, they're all adjacent to V via those colors. And so this is adjacent to V via red and adjacent to V via blue. Now, how could I possibly use this interesting fact? Well, I'm supposed to conclude that I can find a red KS or a blue KT. How could like having a bunch of stuff here which is adjacent to V via red possibly help me? I want to get more people involved in this because it's a neat fact which is actually not crazy. I'm just like, it's going to be really handy that all of these vertices over here, I'm going to select them. All of those are adjacent via red. All of these are adjacent via blue. And if my goal is to get a red KS or a blue KT, somehow the fact that in this zone they're all already red to there is handy. Why so? Can anyone tell me like a reason why if I have enough of stuff here, I'm in good shape? And why anyway is this rs minus 1t, rs t minus 1? Why is there a minus 1? How do I use the minus 1? Oh, remember, what those mean is that each of those are numbers for which in that, if you have that many vertices, bang, you definitely have a red K, s minus 1 or a blue kt. As soon as you get that many vertices, you have to find some structure like that. Chris?
So you connect those two blobs downwards so that they're not going to create triangles. But then if you remove the v, those edges have to go somewhere no matter what if you make another triangle.
Okay, so now, one thing here is that if you're thinking about like the triangle world, right? In the triangle world, it's like, whoa, we already know a lot about like colors. If we were trying to avoid monochromatic triangles, it's like, what in the world am I going to do? I have no good way to connect. But I want to take this moving out of triangles a little bit, because the place we've moved to is now like KS's and KT's. So I'm glad you said the idea. We need to have a lot of ideas to solve this. Sean?
It's like our first one, like the red circle will be rs minus 1t, and then we're going to like supplement that s minus 1 with like the red connection to v.
Okay.
And then that's going, and then like the same thing for the blue one.
Let me digest that one piece out. I think what you said is if you found a red ks minus 1 up there, you got your red ks. Is that what you just said?
Yes.
If you find a red ks minus 1 here, then you plus the v, and you got your red ks. That's actually why this all being red is handy. It's like, now I'm happy enough in here. It's like, my goal was to find a red ks or a blue kt. Well, by doing this divide and conquer, I suddenly said, in this place here, I don't need a red ks anymore. A red ks minus 1's enough, because I'm going to add one more to finish it. So if I had this, then plus v, let me just write with more space. If I find this, then adding v gives a red ks. So that means that I only need to guarantee inside this zone a red ks minus 1 or a blue kt. So what that means is, so if this is at least Ramsey number s minus 1 comma t, I'm done. That's one of the important points. Are people okay with this? It's like, as soon as I have enough vertices to guarantee a red ks minus 1, which I'll add the v to, got red ks, or if I get a blue kt, well, got it, blue kt, that's it, I'm done. Then I'm good. Okay. Well, if that's the case, the same argument tells me something down there. Can anyone tell me what that argument would be? Or what the bound would be? I just want to make sure everyone's on the same page. Under what circumstance can I also say done as long as this bottom blue blob is big enough? Brayden.
As long as you have more s t minus 1 vertices in that section, essentially just using the same argument, say that there's either an s group or t.
Yep. So on the other hand, if I got the other one to be big enough to get a red ks, thank you, or a blue kt minus 1, use v. Now I got a blue kt. I'm good. Oh no. But how are we done? So what am I supposed to do? I'm supposed to somehow show that, well, at the beginning I started with this many vertices. I started with the two Ramsey numbers added together, rs minus 1t plus rs t minus 1. I started with those two numbers. I'm seeing the numbers appear again, which is exciting. I would like to get some conclusion that says at least one of them has to happen. How do I finish this? We have all the pieces in front of us now. We even have those particular Ramsey numbers which appear there. Anyone else want to jump in? I like to involve as many people as we can on this. I'm starting with all of this stuff. If I can get either this or this big enough, I'm done. How do I know that one of them has to be big enough, or both? Jack.
I don't really know how to say this, but again, the supposition is that if there's at least, for example, the red one, r s minus 1t, right, then we're done. But the other case is that it's not true. In which case, that the other pile is going to have, I think this is true, right? That the other pile is going to have the amount we wanted, right? Because the total is that.
Okay. You're on the right track. You're on the right track, okay? You're absolutely on the right track. And this is like slightly tricky, which is why I just wanted everyone to think through it together. You're absolutely on the right track. It's like, this looks suspicious. I've got the two numbers that add up to there. Should be some kind of a running out of space issue. The only thing to be careful is that one vertex got yanked off here. So the easiest way I usually explain this is I say, well, let's do like a proof by contradiction in the sense of, if I could get this, I'm done. If I could get this, then I'm done. Whenever you're doing a proof, if you got to the, if I got this, then I'm done, then you're always able to say, well, suppose I'm not done, then not that. Is that okay? So I'm going to say, well, that's true. If it's this, then I'm done. How would I not be done? The only way you can not be done if it's less than that. But here's where we're going to overcome the one. Maybe Advait, this is probably what you wanted to say. Can you help me out with that?
Yeah, I was going to say, suppose neither of them were the right size, then there's at least, then there's at most like r of s minus 1t minus 1 in the first one.
Yes.
R of s t minus 1 minus 1 in the second one. And then you add the one vertex back and then you don't add it.
Yes, that's the key. The key is that the minus ones are perfectly lined up to give you the proof. The point is, all right, well, that would be done, but otherwise, what's the deal? Otherwise, it's like, I have less than or equal to that minus 1. And the same thing would happen over here. It's like either I'm done, or the number of things in the blue is this nice r s t minus 1, and then minus 1. But then how many vertices are there in total if I do that? Well, I get the two nice r things which I wanted, a minus 1, and then a plus 1 for this vertex v, which is just 1 short. Did that make sense to people? So I have this then done. And maybe I'll just like write up here, okay? So it's like continuing up here. So if not done, then the number of red, well, I'll just write the number of vertices that we have is less than or equal to 1, that's for the vertex v, plus r, I'll use colors, plus the Ramsey number, r s minus 1 t minus 1, and then plus, using the blue, r s t minus 1 minus 1. My pen ran into the right side. Minus 1. There. Minus 1. Okay? And that's just like too little. I'm short by exactly 1, which is too small. We were supposed to start with, without the minus 1. Okay, so we've just proven this. And it's just perfect with the minus 1. Now, there's a reason why this is really satisfying. It's because this actually is a nice recursion. You know what this means? If I'm going to do some induction thing, and somehow r1 comma t is 1, rs comma 1 is 1, and all of these rst's are less than or equal to rs minus 1t plus rst minus 1. Have you seen anything else in this combinatorics class where you like have a function of two variables, and the function of the two variables depends on what happens when you reduce one of them by 1 and reduce the other by 1? Actually, that's a pretty bad hint. That's probably hard to see. I'm going to, Braden, maybe you do see. It's like Pascal's triangle is here. That's actually what's going on. Because if I'm going to say that the value of each one, let's just do it real quick this way, okay? So what do I now know? I can make a chart for r, s, t is less than or equal to what? Well, let's make a chart. So here is the s and the t. S can be 1, 2, 3, 4, 5, and so on. T can be 1, 2, 3, 4, 5, and so on. And I'm just writing down upper bounds. So I'm saying these are all at most 1, these are all at most 1. But now the fun begins. Because what I do is if I want to know what is the Ramsey number of this less than or equal to, is less than or equal to what happens when I decrease each of s and t by 1, and you add them together. Did this sort of make sense? Like, that's exactly what r s minus 1t and r s minus 1t is this way, and r s t minus 1 does. And if I want to know what to write here, well, that's going to be whatever was above and whatever was to the left added together. These are not the Ramsey numbers. These are upper bounds on the Ramsey numbers. But look, we've seen that before. That's just Pascal's triangle. This was like on the early part of the class. And here for like the 3 and the 3, what goes here is the sum of those. 3 plus 3 is 6. Does this make sense? So actually, this is nice. We just found out there's a bound on Ramsey numbers. It has something to do with Pascal's triangle. And this actually shows R, S, comma, T is at most some choose thing. And it turns out to be S plus T minus 2, choose S minus 1. Very satisfying. That's very finite. Actually, the word very is uncalled for. It's just finite. All right, finite things are finite. In fact, it's not very finite. It's pretty huge. But what I have here is I've just found out that it satisfies this Pascal triangle thing. And if I was just careful, I would see that this is just S plus T minus 2, choose S minus 1. All right, so we have now proven that the Ramsey numbers exist, and therefore we can now wonder how big they are. And we'll continue with that on Monday. See you guys.
Thank you.
Yep.